Limits of functions is a concept that we already know from calculus, but let's make it more formal in the context of metric spaces. So let's say we have two metric spaces x and y. And let's say we have some function f that goes from E contained in x to the metric space y. So this function f is mapping E into y. Now, let's say P is some point that is a limit point of E. So we are going to write limit of f of x as x tends to p equals q, or more informally, we will sometimes write f of x tends to q as x tends to p. Okay, so the definition of this limit is going to be that there exists some point q with the following property. For every epsilon bigger than 0, there exists delta bigger than 0 such that if the distance between f of x and q is less than epsilon for all points x in E, for which the distance between x and p is less than delta, and this is the distance in the metric space x. Okay, here it's important to notice that x and y don't need to be the same space. Okay, it could be different spaces with different distances, different metric spaces with different distances. Even if we are used to see real functions that go from the reals to the reals. Okay, so again, here what we are saying is that given any epsilon, there exists some delta such that whenever the distance between x and p is smaller than delta, then we know for sure that the distance between fx and q is less than epsilon. So whenever x is close to p, then f of x is close to q. That's what we are saying. And this is what is known as an epsilon delta definition. Okay. By the way, historic remark, they chose epsilon and delta because they were not so frequently used in math. So basically, whenever you see epsilons or deltas, this is frequently the context. Okay, these are letters that are reserved for continuity and for limits of functions, or in general limits. Okay. So as I was saying, some examples could be x and y, they could be the real numbers, they could be Rk, the complex, any of the metric spaces we have already seen. And in those cases, the distances, dx, dy, will be the corresponding distance, the absolute value, the modulus, the square root of the sums of the squares, and so on. We have seen so many. Now, one small remark. Notice here that I mentioned that P is a limit point of E. Doesn't necessarily have to be a point of E. It could, but maybe yes, maybe no. Okay. So here what I wanted to say is that P is a point in X, but not necessarily a point in E. It could be in the closure. That will be remark 1. Then remark 2 that I want to make, even if P belongs to E, that looks like it would be a much better case. We could still have so let me say, even if P belongs to E, we could still have that f of P is different from the limit as x tends to P of f of x. This definition of limit is very similar to the definition of limits of sequences that we have already covered. Actually, we can rewrite the definition of limit for functions in terms of limits for sequences. So let's just take xy metric spaces, E, F, and P as before, as in the previous definition, and then the limit as x tends to P of f of x equals Q if and only if the limit as n tends to infinity of f of Pn equals Q for every sequence Pn in E such that Pn converges to P and Pn different from P. So basically what we are doing when we take the limit of a function, we are taking a massive sequence in a way. Okay, we are taking actually all possible sequences that converge to the point P. Now, this actually requires a proof, even if it's not very difficult, but it will help us get warmed up with these notions. So let's prove. So it's an if and only if. So let's prove first from left to right. So let's assume the limit of f of x equals q as x tends to p. Okay, and then because we want to prove the right-hand side, okay, here what we actually want to prove is that the limit is q. And this has to be true for every sequence that satisfies this. So that's also something we assume. So we assume that the sequence Pn in E is such that Pn converges to P, Pn different from P. Okay. So these are the two things that we can use, and what we want to show is that the limit of Fpn equals Q as n tends to infinity. Okay, with this clear, we just need to use the definitions. So in the definition of convergence for a function, of a limit of a function, and also in the limit of a sequence, there is a prominent, the epsilon has a prominent place, right? So first thing we need to do is to take some epsilon, okay? So given epsilon positive, then we know that there exists some delta, okay, such that the distance between f of x and q is less than epsilon, remember these are in the space y, so it's the distance in y. If this distance is smaller than epsilon, if several things happen, x is in the domain, and the distance between x and p is less than delta. Obviously, the distance also is positive. Okay, as in the definition, that means that the 2 points are different. Now, this is one side, and then the other thing that we have is that Pn converges to P. Okay, so what we can get from there, since Pn converges to P, then for the same epsilon, there exists some capital N, okay, such that N bigger than capital N implies that the distance in x between Pn and P is less than delta. Okay, so when we put the two things together, you see here we already have the same condition. Okay, there exists a delta. So here what we want to do then is say, well, okay, so for n bigger than capital N, we have that the distance in y between f of Pn and q is less than epsilon. And that is what we needed to show that the limit of fPn is equal to q. Okay, you see here we are basically saying that the distance between fPn and q is as small as we want. Okay, as long as n is large enough. Okay, so that's half of the proof. For the other half, we could just assume that the limit of fPn as sentence to infinity is equal to q. But an equivalent way to prove this okay, so an equivalent way to prove this is to assume, so we are proving, this is a side note, okay, so we're proving A if and only if B, A implies B, this is done, and then we want to show that B implies A, okay, but for this one, something that is equivalent, let me write, is to show that not A implies not B. Okay, so this is what we are going to do. This is logically equivalent. What we are going to do is show that if we assume that the limit of f of x as x tends to p is different from q, okay, then we are going to show that the limit as n tends to infinity, there we go, n tends to infinity f of Pn different from q for Pn such that Pn converges to P, Pn different from P. Okay, so here it's important that the Pn is one of the sequences in the theorem, okay, because if it's not, then we are not doing anything. But then what we are saying here is even if the sequence is one of the sequences in the theorem, the conclusion still not holds. Okay, so yeah, so with this assumption, let's show the second part. So limit as x tends to p of f of x different from q, this means okay, that there exists some epsilon, okay, because the definition says for every epsilon. So the negation is there exists some epsilon such that for every delta, okay, this is the negation of there exists delta. For every delta, there exists a point x in E, and this one will depend on delta. There exists a point x such that the distance between f of x and q is at least epsilon. Okay, but the distance between x and p is less than delta. Okay, so here what are we saying here? I'm missing the 0. Okay, there we go. What we are saying here is that even if x is very close to p, f of x is not close to q. Okay, there is that epsilon, there is like a neighborhood around q that doesn't let f of x in. Okay, and now once we have this, it's just a question of taking, you see, because it says for every delta. So now it's your choice. So take delta n, which is equal to, let's go with the easy ones, 1 over n, n 1, 2, 3, and so on. And then like this, we find to find a sequence. This way we find a sequence in E satisfying the condition, this condition over here. Okay, such that the limit of fpn as n tends to infinity is different from q. Okay, so this way, since the negation here is so massive, it's like for every delta, there is no way. So then you just pick a delta that is convenient, and then that will give you a sequence of points in E. Okay, you can just pick any point, and then with that you have the negation of the second part, and that finishes the proof. Now, one important consequence of this theorem is that the things we know for sequences, we can translate them into limits for functions. So here, for example, if you remember from sequences, the limit of a sequence was unique, right? So same thing here. If f has a limit at p, this limit is unique. Again, this follows because the limit of a function is equivalent to a limit of a sequence, and the limit of sequences, it's unique.